Hello students, welcome to section 8-2, Solving Exponential Equations and Inequalities. So solve exponential equations. All the properties of rational exponents that you know also apply to real exponents. Remember that a to the m times a to the n is equal to a to the m plus n. That's one property to remind yourselves of. So is a to the m all raised to the n, which results in a to the m n. As is a to the m divided by a to the n equal to a to the m minus n power. Property of equality for exponential functions: if b is a positive number other than 1, then b to the x equals b to the y if and only if x equals y. So for example, solve for, and I've circled the base, raised to the x minus 1 equals 2 raised to the x plus 5. I circled that base as well. Now our goal should be to equate our exponents, but only after we get the bases to be equal to each other. Right now 4 and 2 are not the same base, so we're going to go ahead and rewrite, as they explain here, rewrite 4 as a base of 2, or 2 squared technically. So the left side will be rewritten as 2 squared, and then you still then have x minus 1 in parentheses next to it. And that is equal to 2 to the x plus 5. Now that the bases are identical, we can proceed by setting 2 parentheses x minus 1, as you see in the next step, equal to x plus 5. This is the property of inequality for exponential functions, as we just denoted up above. Okay, or equality technically, as it should state. So that's a typo I'll have to fix. We'll go ahead and distribute the 2, so you'll see 2x minus 2 equals x plus 5. Add 2, subtract x, so x simply is equal to 7. One thing that I encourage you to still do here, though, is to double check to see if your answer works. In other words, plugging in 7 here for x and 7 there. So 4 to the 7 minus 1, or 4 to the 6th, should be in fact the left side, and it equates hopefully as such on the right side, where it's 2 to the 7 plus 5, or 2 to the 12th. So if you double check to see if you're on track, it should end up being the exact same number. So we've done it correctly. Example 2, write an exponential function whose graph passes through the points 0, 3 and 4, 81. I've denoted xy here as well as xy there. The y-intercept is 0, 3, and that's fantastic in the context of easily being able to find the other values in context. I'll give you the first equation as such, or highlight it, where y equals a times b to the x. Note that this is the original kind of general form to relate to. If I plug in 3 for x, or pardon y, and if I plug in 0 for x, we don't know a nor b. However, b to the 0 is nicely just 1, which is great because, again, knowing the y-intercept dictates that the a value nicely is just 3 in this case, so a equals 3. Once you assess that a is equal to 3, your second equation, which uses this second point, 4, 81, 81 again is y, and that is equal to 3, which is now a, times b to the 4th power. We're substituting 4 in for x here. We can solve for b simply by dividing both sides by 3, so 81 thirds, and then we'll take the 4th root of both sides. 81 thirds ends up being 27, so the 4th root of 27 is your b value. In other words, 2.280 if you double check. The final answer, simplified, at least in the context of a and b rounded, looks something like this. Y equals 3 times the quantity 2.280 to the x power. If we wanted to double check again on the calculator to ensure that these values make sense, I do want to use 3 as a. And instead of the decimal 2.280, how about I use the 4th root? So math, option number 5, and I'll do the 4th root of 27. This will just essentially ensure that whatever I plug in then for x, that it makes sense. Now the parentheses here maybe I can delete. I don't technically need those. I will need them here, however, because then I'll raise this to any power that you can imagine. Let's start with raising it to the 0 power maybe. Not surprisingly, if you plug in a value of 0 for x, you better end up with 3, and you do, so 0, 3. Similarly, if you go ahead and plug in a value like 4 for x, you should end up with, not surprisingly, 81, because again, 4, 81 was another point on the function. So this simply is, in fact, just an exponential growth function, which happens to pass through those 2 points. Okay, moving on. So we're going to solve, and we're going to go ahead and do some other analyses on the bottom, as you can see, 10, 12, and maybe 17. Starting off with number 1, we're just solving. So we have 3 to the 2x minus 1 equals 3 to the x plus 2. Because the bases are identical, we can easily, again, using the property from up above, equate 2x minus 1 and x plus 2. So 2x minus 1 equals x plus 2. Algebraically, subtract x, add 1, so x equals 3. And certainly you can check your answer. The next question, number 2. 2 to the 3x equals 4 to the x plus 2. I won't do anything to the left side, leave it as 2 to the 3x, but on the right side, you do need to rewrite it such that it's the same base. So of course 2 squared, because that's 4. 2 squared again though, x plus 2 in parentheses. Now that the bases are the same, we can equate 3x and 2 times the quantity x plus 2, which is going to be 2x plus 4 simplified. In this equation you can see now algebraically subtracting 2x to get x, therefore x is equal to 4. Number 3. 3 to the 2x minus 1 equals 1 over 9. 3 is a base that I cannot simplify. I can't manipulate this any farther, but what I can do is I can turn 1/9 into 3 to some power. Now think of it this way. 3 to the negative power is the same as 1 over 3 to that number as a positive exponent. And if you raise 3 to the negative second power, that will take its reciprocal and become 1 over 3 to the positive second. So 1 over 3 squared, of course, is 1 over 9. Now the bases are the same, which is again my initial goal, and because that's the case, I can set 2x minus 1 equal to negative 2. From here I can add 1, I can divide by 2, so my final answer is nicely just x equals negative 1/2. Let's take a look at another problem, and then we'll jump down to 10 through 18. Number 9 is a great one to finish up with here. Number 9, you see on the left side 1/64 to the x minus 2 power, and that equals 16 to the 3x plus 1 power. 1/64 can be and should be rewritten as 2 to some power because 16 can also be rewritten as 2 to some power. So if we take this and write it as 2 to the negative 6th, and yes, 2 to the negative 6th is in fact 1/64. Actually, let's do 2 to the positive first. So of course 2 to the negative 6th will be its reciprocal, 1 over 64. Okay. And if we double check, converting of course, we see that's the case. Okay. So we know that 2 to the negative 6th is 1/64. That's great. We just rewrote that particular number. And then 16, well, that's 2 to the positive 4th. 2 to the 4th, if we double check, we'll see that to be the case. Obviously, 16. Okay, so we have 2 to the negative 6 times the quantity x minus 2, and 4 times the quantity 3x plus 1. So we have a negative 6x plus 12, and that equals 12x plus 4. Adding 6x to get 18x, subtracting 4 to get 8, dividing by 18. 8/18 is reducible. Dividing each by 2, would work nicely where 4/9 is your final answer. So 4/9, and that covers that. 4/9 is the value for x, and you could plug it in again if you'd like to check later. Write an exponential function for the graph that passes through the given points. I'm going to go ahead and take a look here at, let's take a look maybe at number 10. We know 0, 4 is the y-intercept. We know 236 is another point. X, y, x, y. So the first equation is as easy as plugging in 4 for y, plugging in 0 for x, and remember this is the equation that we're referring back to, substituting again for y and for x there. B to the 0 is 1, so a nicely is just 4. The second equation we set up uses this y, so 36, there it is, equals 4, which is again now your a value, and that equals b to the second, which is the x coordinate, right? So b to the second. Divide both sides by 4, nicely enough you get 9, take the square root of both sides, and you'll end up with b equals plus or minus 3. Now if you look at the answer key, you will end up seeing that y equals 4 times positive 3 raised to the x as your final answer. It should work out too if you double check that negative 3 is also going to be a function of which these 2 points go through. However, we're not going to count negative 3 in our solution set because b as a base needs to always be positive, and it's either between 0 and 1 or it's greater than 1. In this case 3 is greater than 1, so we will rule out that particular answer. And I think what I'll do is I'll actually just cross it off because we won't count that negative solution. Again, b is positive in our solutions that we've seen. Can be technically a fraction, but it can't be negative. Okay, so let's move on to the next page. I do want you to try 12 and also 17 on your own, and also any of those other questions that we didn't get a chance to take a look at prior to those, 5 and 7 for example. Please try those on your own. On the next page, we're going to go ahead and solve exponential equations and inequalities continued, more specifically inequalities. An exponential inequality is an inequality involving exponential functions. Property of inequality for exponential functions: if b is greater than 1, then b to the x is greater than b to the y if and only if x is greater than y. And if b to the x is less than b to the y, if and only if x is less than y. And if you look at the inequalities, they actually match up quite nicely. Greater than, and then here, less than, less than. And again, b must be greater than 1 to start. Please note this. Okay, as we continue through here, I would like for us to take a look. I'd like for the first example right off the bat to be noted where on the right side of the inequality, you should, I would argue, pretty nicely be able to rewrite it as, well, 5 to some power. In this particular case, it should be denoted as 5 to the negative third. So as you see, 1 over 125, 1 over 125 ends up being 5 to the negative third. And then from there, you hopefully can see the continuation of which, well, it turns out you have 5 to the negative third equals 5 to the 2x minus 1. And from there you can take the exponents and simply set them, at 2x minus 1 greater than negative 3. To solve this, it's as easy as adding 1 to get negative 2, dividing by 2 to get negative 1, and therefore x is greater than negative 1. So it says that the solution set is x such that x is greater than negative 1. One thing that I want us to take a look at and be mindful of as we finish this is the aspect of how this would look in interval notation. So if we're rewriting this in interval notation, let's pay attention to how that's going to essentially change kind of the look and feel of it. So if we take a look, we'll go ahead and rewrite this as such. So I can, and hopefully you recall, taking the quantity negative 1 with a parentheses because it can't equal negative 1. And because that's the case, but of course it's greater than, we'll say negative 1 to infinity. Okay, let's continue. Number 1, following exercises just below here. We take a look. As you can see, we can maybe rewrite the left side, pardon, the right side of the equation, because the left side can't be manipulated. But the right side can. Turns out 3 to the third power is 27. So 3 to the negative third power, not surprisingly, is 1 over 27. So if we set x minus 4 equal, or in this case technically greater than the other on the side, negative 3, here's our next step. So x minus 4, or pardon, less than, if I said greater than, I meant less than negative 3. We can add 4 to both sides, so simply x should be less than 1. And if we're going to write this in an interval notation form, it should be parentheses, negative infinity to 1. Remembering again that 1 can't be part of the solution set, so we use a parentheses. So that's the solution for that particular question. Let's take a look at more problems later on when we're together, but please take a look at some other questions and compare those maybe to the answer key. We will continue this another time.